Dear students, in this class we will be learning about infrared or IR spectroscopy and rotational spectroscopy. This is your syllabus, and under the title of infrared spectroscopy you have to learn about the vibrational degrees of freedom, types of vibrations, that is symmetric and asymmetric stretching and bending, then calculation of force constant, concept of group frequencies, that is frequencies of common functional groups in organic compounds, and also the speciality of this fingerprint region of this infrared spectra. And in rotational spectroscopy you have to learn about the rotational spectra of diatomic molecules and determination of bond length using the data of rotational spectra. Please take the section vibrational spectroscopy in your text. So vibrational spectroscopy, this is the same as infrared spectroscopy because vibrational transitions are brought up by the absorption of radiations from the infrared region of the electromagnetic spectrum. So vibrational spectroscopy involves the study of transitions between quantized vibrational energy levels of a molecular species induced by the absorption of infrared radiation. So this vibrational spectroscopy is arising from the absorption of infrared radiation by molecules, and this involves the transitions between the quantized vibrational energy levels. So this is the key principle of vibrational spectroscopy, and the infrared region can be divided into three regions, that is near infrared, middle infrared and far infrared. The infrared region is entirely covering from 50 to 12,500 centimeter inverse, or in the scale of nanometer we say it covers between 2000 to 800 nanometer range, and this range is subdivided into three regions. That is, first is the near infrared region. Near infrared means it is ranging from 4000 to 12,500 centimeter inverse, or in terms of nanometer we say it is ranging from 2500 to 800 nanometer. In the middle IR region, middle infrared region is from 667 to 4000 centimeter inverse, or from 15,000 to 2500 nanometer. And the far infrared region is from 50 to 667 centimeter inverse, or we can say it is from 2 lakh to 15,000 nanometer. So these are the three divisions of the infrared region in the electromagnetic spectrum. And we must note that the middle infrared region, that is the region ranging from 15,000 to 2500 nanometer. This middle infrared region covers most of the vibrational transitions occurring in molecules. Now let us learn more about the vibrational transitions. So the molecular vibration in which all the atoms oscillates with the same frequency and pass through their equilibrium positions simultaneously is called a normal mode. So define a normal mode of vibration. A normal mode means in any molecule there is a normal mode of vibration. So normal mode means that particular molecular vibration, that particular mode of vibration in which all atoms of that molecule oscillate with the same frequency and pass through their equilibrium positions simultaneously. So in a diatomic molecule can have only one normal mode of vibration. A diatomic molecule means a molecule having only two atoms. Okay, for example, a carbon monoxide. Okay, so it can have only one normal mode of vibration, and this normal mode of vibration takes place along its bond axis. So every molecule will be having a bond axis. So normal mode of vibration takes place along this bond axis. So let us see the different types of vibrations. There are two kinds of fundamental vibrations in the molecule. First is a stretching vibration and second is the bending vibrations. So a stretching vibration means in this type of vibration the distance between two atoms increases or decreases. So if it is increasing, we say it is stretching, and if it is decreasing, we say it is compressing mode. So in this type of vibration, two atoms, the distance between two atoms either increases or decreases, but the atom remain in the same bond axis. So the equilibrium position, along this equilibrium position, the atom will vibrate, and this vibration corresponds to one-dimensional movement. So an example is given here. This is a molecule, a carbon dioxide molecule, and the stretching vibrations of carbon dioxide molecule is represented in this figure. So first is the symmetric stretching vibration of carbon dioxide molecule. That is, both the oxygen atoms are moving in the same length towards the same extent but in opposite directions. And second is the asymmetric stretching. In asymmetric stretching, one oxygen atom is moving away from the carbon atom while the other oxygen atom is moving towards the carbon atom. So there is an overall asymmetry in the molecule. So first is the symmetric stretching and second is the asymmetric stretching. So in symmetrical stretching, both the atoms move in and out simultaneously. And in asymmetrical stretching, one atom moves in while the other moves out. Another example is also given. So this represents a V-shaped molecule. For example, let it be a water molecule. Okay. So in this case also we can see that the first is the symmetrical stretching. That is, the two atoms at the end is moving towards the same extent from this central atom. So this is symmetrical stretching. And second is the asymmetrical stretching. While one atom is moving towards the central atom in this V-shaped position, the other atom is moving or stretching away from the central atom. So this is a asymmetrical stretching mode. The second type of vibration is the bending vibration. So let us see about bending vibrations. In this type of vibration, the position of atoms changes relative to the original bond axis. That is, bond angle changes. So bending vibrations require lesser energy and occur at longer wavelength regions. So bending vibrations, when compared to the stretching vibrations, it requires lesser energy. So this type of vibrations will be occurring at a longer wavelength region or a shorter frequency region, because the energy required for this type of vibration is lesser compared to the stretching vibrations of that molecule. So a bending vibrational mode in which the atoms remain in the same plane as the nodal plane of the system is called the in-plane bending vibration. So now you know that the bending vibrations can be in plane or it can be out of plane. So from this we have to understand that the stretching vibrationals are one-dimensional, whereas the bending vibrationals are two-dimensional in nature. So the bending vibrations are either in plane or out of plane. And the in plane bending vibration, there are two types of modes, that is the scissoring mode or the rocking mode. So in a scissoring mode, both the atoms swing in concert towards opposite directions. Okay, so you can imagine the direction of movement of a scissors. Okay, so in similar way, the molecules will vibrate. That is the bond angle will change in bending vibrations. But all the atoms will be in the same plane. So that is why it is an in-plane bending vibration. And in a rocking mode, both the atoms swing to the same side and then both to the other side. So in this figure, you can see a symmetrical or out of plane bending and an asymmetrical or out of plane bending. Then a symmetrical in plane bending, that is the scissoring mode, and the asymmetrical in plane bending, that is the rocking mode. Okay, so the first one we studied was about the in plane bending. So the in plane bending is represented by this third and fourth picture in your text. This is a scissoring mode, that is both the atoms are moving towards each other. Okay, and in the rocking mode, this atom will be moving in this direction and this atom will be moving in this direction. So all the three atoms will be in the same plane itself, but there is difference in the direction of motion of these atoms at the corners. Okay, now let us see about the out of plane bending. When both the atoms bend out of the nodal plane, the bending mode is called the out of plane bending. So we have to consider the nodal plane of this molecule, and when both the atoms are moving out of plane, that is out of this nodal plane, we have to imagine a nodal plane here, a nodal plane passing through this molecule. Okay, and when these atoms are moving, both these atoms will be extending out of this nodal plane. In that case, we say that this vibration is out of plane bending. And there are two types of such out of plane bending, as you can see here. So first one is the twisting mode. In a twisting mode, one atom swings up and the other swings down related to the plane of the paper. So this is a twisting mode of representation. Here one atom will swing up of this nodal plane, and while this other atom, that is the third atom at this corner, will swing down. Okay, so this is out of plane, a twisting mode of vibration. And the second is the wagging. So in a wagging mode, both the atoms swing up and down of the plane of the paper in harmony. So simultaneously these two atoms will swing either up or above the plane, nodal plane, or below the nodal plane. So this is the out of plane bending, or it is also called as wagging. Okay, so twisting is actually asymmetrical out of plane bending, and wagging is symmetrical out of plane bending. Similarly, in the case of in plane bending modes, this scissoring mode of vibration is symmetrical. Okay, it is symmetrical because if we divide this molecule along a nodal plane like this, the bond angle will not change to much extent. So the molecule will remain symmetrical. Okay, and whereas in the case of this rocking mode, it is an asymmetrical in plane bending. So you have to understand the concept of in plane and out plane bending and the types of bending modes. Similarly, in the case of stretching mode, we learned about symmetric stretching and asymmetric stretching. And also, in the case of symmetrical stretching, you have to understand that there is no change in dipole moment of the molecule. Okay, so there is no change in dipole moment of the molecule in the case of a symmetric stretching or symmetric stretching vibration, whereas in the case of asymmetric stretching, the dipole moment of the molecule is changing because the molecule is losing the symmetry and there is a change in the distribution of electron density around these bonds. So these two CO bond will not be identical. In that case, the dipole moment of this molecule, when it is in asymmetric stretching mode, it will change. Now let us learn to calculate the vibrational degrees of freedom of a molecule. Vibrational degrees of freedom. So polyatomic molecule having n atoms have more number of normal modes. So here capital N is representing the number of atoms present in a particular molecule. So first case is of a linear molecule. In the case of a linear molecule, for example a carbon dioxide molecule, it is linear in shape. So in this case there are 3n minus 5 normal modes of vibrations. So if you want to calculate the total normal modes of vibration of a carbon dioxide molecule, you can substitute the number of atoms, that is for carbon dioxide capital N will be 3, okay, CO2 molecule. Then you will get the normal modes of vibration of a carbon dioxide molecule from this formula. And in the case of a non-linear molecule, for example a water molecule, it is a non-linear molecule, and in this case 3n minus 6 normal modes of vibrations are there. So the formula is different for linear and non-linear molecule. For a non-linear molecule, the equation is 3n minus 6, whereas for a linear molecule it is 3n minus 5. And a molecule with n atoms have n minus 1 bonds between its atoms. So it will have n minus 1 stretching vibrations and the rest will be 2n minus 5. Okay, 2n minus 5 bending vibrations out of this 3n minus 6. This is for a non-linear molecule. Whereas for a linear molecule, if a molecule is having n atoms, then there will be n minus 1 stretching vibration and the rest 2n minus 4 bending vibrations out of this 3n minus 5 normal modes. So the vibrational modes of water molecule is given here. So water molecule is a non-linear molecule and it will have 3n minus 6, that is 3 into 3 minus 6 is equal to 3 fundamental vibrations. So calculate the fundamental vibrations of a water molecule. You can expect questions like that. So you have to first understand that water molecule is a non-linear molecule and you have to use the formula 3n minus 6 for non-linear molecules and substitute the total number of atoms in that molecule in this formula. So for a water molecule you will get 3 fundamental vibrations. So it is represented here. So there are 2 stretching vibrations, that is a symmetric and an asymmetric stretching vibration, and then 1 bending vibration. So in the case of stretching vibration, the bond distance will only be changed. Okay. In symmetric stretching, both the OH bonds will be extending in the same direction. Okay, it will be stretching in the same direction. So it is a symmetric stretching. And in asymmetric stretching, one hydrogen will be moving towards the oxygen while the other hydrogen will be moving away from the oxygen. So this will be an asymmetric stretching mode. So in these 2 cases, the bond length or bond distance is only changing and there is no change in the bond angle. And when we talk about this bending vibration, so this is a symmetric bending. Okay, symmetric, in the case of a symmetric bending vibration, both the hydrogen is moving either away or towards each other. So here the bond angle will be changing. So these three are the three fundamental vibrations or normal modes of vibrations in a water molecule. And a normal mode of vibration is one in which all atoms in a molecule vibrate at the same frequency and are in phase with each other. So this is the diagrammatic representation of three fundamental modes of vibrations of water molecule. And when you draw this fundamental vibration, it is important that you represent this motion, direction of motion using this arrow. Okay. Next is the vibrational modes of carbon dioxide molecule. So a carbon dioxide molecule, as we have discussed earlier, it will be having a total of 4 fundamental vibrations. Okay, so this is a linear triatomic molecule. It is in linear shape. This is a bond axis. Okay, the bond axis is passing through all these 3 atoms. You can imagine a bond axis like this. So along this bond axis, the in plane, so this type of vibration is actually either in plane or out of plane. Okay, and there is also a stretching as well as bending vibrations. So let us see the different types of vibrations here and how we will calculate the vibrational modes of carbon dioxide. So for calculating this vibrational modes of carbon dioxide, you have to use the formula 3n minus 5. It is because it is a linear molecule. Okay, and you have to substitute the value of n here. N is the total number of atoms in the carbon dioxide molecule, and you know that n is equal to 3 here. So the formula becomes 3 into 3 minus 5. That is 4 fundamental vibrations are present in carbon dioxide molecule, which is represented here. So let us see each one. The first is the symmetric bending in the plane of paper. Okay, this is the symmetric bending. So you can imagine a plane, that is the plane of the paper here, and you are placing a carbon dioxide molecule like this. So in the in-plane bending, what happens is 2 oxygen atoms will move towards each other and the carbon will be moving upward. But remember, all the 3 atoms will be in the plane of the paper itself. Okay, so that is why the bending is in plane. And this type of vibration is IR active. Okay, that is, it will give an IR peak or peak in the infrared spectrum. It will absorb, for this particular vibration, it will absorb energy from the particular region of the IR spectra, IR electromagnetic spectra, and it will give a peak. And the second is the symmetric bending perpendicular to the plane of the atom. Okay, so this is the second one. This is the symmetric bending, and this is also IR active. Okay, and third is the symmetric stretching vibration, and in this case also you can see the bond is stretching in the opposite direction towards the same extent. So this is a symmetric stretching vibration, but it is IR inactive because the dipole moment is not changing. Since the dipole moment is 0 and it does not change during this symmetric stretching vibration, the mode of vibration is IR inactive. So you can expect a question like which mode of vibration of carbon dioxide is IR inactive, or why the symmetric stretching mode is IR inactive? Because there is no change in dipole moment. The net dipole moment is not changing because the molecule is stretching symmetrically. So only if there is a change in dipole moment, the molecule will absorb a radiation from the IR region, and it will show a peak in the IR spectra. So in the case of carbon dioxide molecule, the symmetric stretching mode is IR inactive because there is no change in the dipole moment. And the fourth mode is the asymmetric stretching. So asymmetric stretching is represented here. So asymmetric stretching is also IR active. So among the four modes of vibrations, 3 are IR active, whereas 1 is IR inactive. So next is the vibrational energy. So how will you calculate the vibrational energy of a molecule? So you have to consider a diatomic molecule like this. So that is a molecule having 2 atoms. So the mass of each atom is represented as M1 and M2, and it is joined by a bond vibrating back and forth relatively to the center of mass. That is similar to a simple harmonic motion. So you have to understand this picture, and this picture is representing 2 atoms, M1 and M2, mass, and it is connected by a bond, and these 2 atoms are vibrating or moving back and forth relative to the center of mass. That is, it is similar to a simple harmonic motion or SHM. And let us assume that one of the atom, say the heavier one, is mass M1 and is anchored. So this heavier atom is anchored and the other is moving either towards or away from it. Let us assume like this. So in the figure, REQ represent the equilibrium internuclear distance. This is the equilibrium internuclear distance, that is the distance from the center of mass of each atoms. So REQ is the equilibrium internuclear distance, which is called the bond length and corresponds to the energy minimum. So at REQ, the energy will be minimum. So suppose if this REQ is shifting, that is the distance between the bond is the atom is increasing, it means that the potential energy of that bond is increasing. So an increase in internuclear distance R increases the potential energy of the system. So this is the formula for the vibrational energy. Vibrational energy E is equal to minus half K into R minus REQ the whole square. So assuming the molecule is a simple harmonic oscillator. So we have to assume that this particular diatomic molecule, it is a simple harmonic oscillator, and then its vibrational frequency, it can be represented as mu OSC. Okay, and this is given by the classical mechanical expression as mu is equal to 1 by 2 pi root of K divided by nu. So the expression for the allowed values of vibrational energy is obtained by solving the Schrodinger equation for a simple harmonic oscillator. Okay, and that vibrational energy is given by this formula, that is EV is equal to V plus half into H by 2 pi root of K divided by mu in joules. So here V is the vibrational quantum number, which can have any values like 0, 1, 2, 3, etc. And H is a Planck's constant and K is a force constant. So we know that Schrodinger equation, there is an eigen value. Okay, so not all values are eigenvalues, but certain values are only selected. So in this case, in the case of vibrational energy, the eigenvalue is given from this expression. Okay, EV. So here there are certain selection rules for vibrational spectra. We know that vibrational spectra is obtained from the transitions between the vibrational energy levels, that is from V is equal to 0, V is equal to 1, V is equal to 2, etc. But we have to understand that not all transitions are allowed. Okay, not all transitions are possible. Only the transitions which obey this particular selection rule are possible. That is delta V is equal to plus or minus 1. It means that a transition can occur from either V is equal to 0 to V is equal to 1. So in this case, delta V is the difference between this V2 and V1. Okay. So V2 minus V1 will be, that is 1 minus 0, that will be 1. So in the reverse direction also the transition is possible. That is delta V can be minus 1 also. It can be either plus 1 or it can be either minus 1. Let us see another example. A transition from V is equal to 2 to V is equal to 3 is possible. It is allowed according to this selection rule. Similarly, a transition from V is equal to 3 to V is equal to 2 is also possible. But a transition from V is equal to 1 to V is equal to 3 is not allowed according to the selection rule, because in that case the delta V value will be 2. Okay, so it is not allowed. So only the transitions that obey the selection rules are possible. So what is the selection rule for vibrational spectra? Give the selection rule for vibrational spectra. So that is delta V is equal to plus or minus 1. This is the selection rule for vibrational spectra. Next is the force constant. So define a force constant. So when a force is applied along the axis of bond, the atom is displaced from its equilibrium position towards right or left, that is stretching and compressing. And it has a tendency to return to its original position by restoring the force. So this restoring force per unit displacement of a harmonic oscillator is called the force constant K, and its unit is Newton per meter or dynes per centimeter. So in SI system it is Newton per meter, and in CGS system it is dynes per centimeter. And the force constant of a diatomic molecule can be found out by knowing the oscillation frequency. So this is the equation for calculating the force constant from the frequency of oscillation of a simple diatomic molecule. So here K is equal to 4 pi square C square mu square into mu. And K is a measure of the bond strength. So what is the significance of this force constant? It is a direct measure of the bond strength of the molecule. And mu is the reduced mass of the molecule, and nu is the vibrational frequency. So once the force constant of a diatomic molecule is calculated, the maximum amplitude of vibration can be calculated. So this is the formula for calculating the maximum amplitude of vibration, that is x max the whole square is equal to h by 2 pi into root of k into mu. So in this next section you have to understand what is meant by 0 point energy. So this is an important concept to understand. So even if the molecule is in the lowest vibrational energy level, that is even if the molecule is having 0 vibrational level, that is V is equal to 0, even in that state the molecule will possess some vibrational energy, which is half h mu. Okay, this is only for a harmonic oscillator. In the case of a harmonic oscillator, even in the lowest vibrational level, the molecule will possess some amount of energy, and this is called the 0 point energy, and 0 point energy is half h mu. So define 0-point energy. 0-point energy is the vibrational energy possessed by the molecule at the lowest vibrational level, that is at V is equal to 0, and it is given as half h mu for a simple harmonic oscillator. Now let us see about the concept of group frequencies. So in a molecule there are different types of chemical bonds, and all these bonds will absorb at a particular frequency in the IR region. So and the bonds in the chemical group may vibrate with frequencies which are almost independent of the remaining portion of the molecule, and such a group will therefore show a somewhat characteristic frequency of the IR or infrared absorption irrespective of the molecule to which it belongs, and this gives rise to the concept of a characteristic group frequency. So if you are taking the IR spectrum of any molecule, we can observe so many peaks in that molecule. Okay, so one such spectrum is given in your text. Okay, so this is a typical IR spectrum of an acetone molecule. So you can see so many peaks here. So all these peaks, it corresponds to the frequency of absorption, the absorption of each type of bonds in this molecule, but it will be either symmetric stretching or asymmetric stretching or bending vibration. There are different types of vibrational modes for the molecule. So all these vibration modes, if it is IR active, then it will give its corresponding absorption peaks. So by observing a spectrum, we can infer which molecule is present, or which type of functional groups are present, what type of bonds are present in that particular molecule. So for a more particular molecule, there will be a particular spectrum, IR spectrum. So all these collection of frequencies at which the molecule vibrate, we can say it is a group frequency. Okay. So application of group frequency in organic chemistry. By recording the spectra of a large number of organic compounds, it has been possible to compile data on the characteristic absorptions of most functional groups. Example, for an isolated carbon-carbon multiple bonds like carbon-carbon double bond or a carbon-carbon triple bond, generally the IR frequency is in this range. That is, a carbon-carbon double bond will absorb at 1650 region, and a triple bond will absorb at 2200 centimeter inverse region. And similarly, a carbonyl group will show a sharp and intense absorption at around 1700 centimeter inverse. So, and another example is an OH group. It will generally absorb around 3600 centimeter inverse. So these are the characteristic IR absorption frequencies of some common functional groups present in the molecules. OH bond, the carbonyl bond, or a carbon-carbon double bond, or a triple bond. So by observing bands in or peaks in these particular regions, we can infer if this particular functional groups are present in the molecule. So such data can be used in the identification of the various groups present in an unknown organic compound through an examination of its IR spectra recorded. Okay. So you can see a table here, and it shows a collection of IR frequencies of some common functional groups. In the case of alkanes, a C single bond, is showing a peak at around this region, that is 2850 to 3000 region. In alkenes, C double bond C will absorb at these regions. So these are the frequency ranges only. So in this range, this particular functional group will show a peak in the IR spectrum. Similarly, you can see the absorption region of this alkynes, that is C triple bond C and OH group, and all these groups are there, so you have to learn these frequencies. Okay, so these are the common functional groups present in organic molecules. Now let us see an important section, that is the fingerprint region. So what is the speciality of this fingerprint region? Okay, so the region between 700 to 1400 centimeter inverse of the IR spectrum is known as fingerprint region. You have to learn this. It's a very important question. Define fingerprint region, or what is the peculiarity of this fingerprint region. Because a fingerprint region, the patterns of vibrations in this region is uniquely characteristic of each molecule. That is, each molecule, like a fingerprint of that molecule, the pattern of vibration at this particular region will be very unique. No other molecule will show the same pattern at this region. Okay, so this is the peculiarity of this fingerprint region. So you can see a spectrum here, and you can identify the fingerprint region from the spectrum, that is the region ranging from 700 to 1400. Okay, so this is the region ranging from 700 to 1400. So this particular region is the fingerprint region of this acetone molecule. So no other molecule will show these characteristic peaks at this region. Okay, but all the other peaks may be shown by other molecules also, but at this fingerprint region is very particular, very special for a single molecule. The frequencies of some of the stretching vibrations, such as C single bond, C N bond, C O bond, etc., and most of the bending vibrations fall in this fingerprint region, which is thus particularly rich in absorption bands. Okay, so these are absorption bands. It is rich in absorption bands, so it is very special to each molecule. Although similar molecules may show very similar spectra outside this fingerprint region, there will always be discernible differences in this region. Okay, and the band pattern in the fingerprint region is very helpful in establishing the identity of an unknown compound. Only a comparison of its infrared spectrum with a set of standard spectra recorded under identical conditions is needed. So this is how we identify a particular molecule, or all the functional groups present in a molecule. We have to record the spectra of that molecule at first, and then we have to compare all the similar spectra in the database. Okay, and then we have to identify which molecule is this unknown molecule. And the concept of group frequencies finds immense application in structural elucidation, particularly in organic chemistry. Now let us see the applications of this IR spectroscopy indeed. So here first is the identification of functional group and structural elucidation. Now if you are considering this entire IR region, IR spectra, it can be divided into two regions. First is the group frequency region, and second is this fingerprint region. So the range of group frequency is from 4000 to 1500 centimeter inverse, and that of fingerprint region is, remember this range, that is 1400 to 700 centimeter inverse. This is the fingerprint region. So in group frequency region, the peaks corresponding to different functional groups can be observed, and from the corresponding peaks functional group can be determined. We can identify which functional group is present in the molecule from this peak present in this IR spectra, IR data of that molecule. So each atom of the molecule is connected by bonds and each bond absorbs at different IR region. So characteristic peaks are observed, and this region of IR spectra is called as fingerprint region of the molecule, and it can be determined by characteristic peaks. And this is the spectra of the acetone molecule. You can observe so many peaks here, and each of these peaks corresponds to the each type of vibrational modes present in this acetone or propanone molecule. So you can identify so many types of bonds here. The first is of course the carbonyl bond, isn't it? C double bond O. And we know that from the table, since this is a keto compound, you can see the C double bond O vibration in a keto compound. Okay, C double bond O stretching mode. So this is coming at this range, that is 1705 to 1725 range. And can you identify that particular peak here? So this is the range. This is a very sharp and intense peak. Okay, so this is the peak of corresponding to a carbonyl function group in this acetone molecule. This is a very sharp and very highly intense peak. Okay, this is a very strong peak here. So similarly, each bond, CH bond or CC bond, all these bonds will show the characteristic absorption peak at all these regions, either in the fingerprint region or in the outside the fingerprint region, that is in the group frequency region. And the second application is the detection of hydrogen bondings. So the OH group is actually absorbing around 3600 centimeter inverse. So here you can see that in the spectrum of acetone, so there is no peak at 3600 region. Usually an OH peak will be a very broad peak like this. Okay, so there is no peak in acetone molecule. You will not find a peak OH peak here in acetone molecule because there is no OH bond here. Okay, so a OH peak, if it is present in a molecule, there will be a strong broad peak at 3600 centimeter inverse, and this OH stretching frequency in alcohols is very dependent on the degree of hydrogen bonding. We know that in alcohol molecule like in ethanol or methanol, there is extended hydrogen bonding. There is so many hydrogen bonding inside the substance. So these hydrogen, because of these hydrogen bondings, the length of this OH bond will weaken. If the since the bond length will weaken, what happens? The vibrational frequency at which that OH bond absorbs energy will also be lowered. Okay, so if the bond length is increased, if the bond length is greater, it means that the bond is weakened, and this in turn leads to a lower vibrational frequency. So thus the degree of hydrogen bonding in alcohol is reflected in the extent of the shift of the OH frequency to lower values. So if a particular alcoholic compound is having a greater extent of hydrogen bonding, then from the shift of this OH peak to the lower vibrational values, we can say that the extent of hydrogen bonding is greater in that particular alcoholic group. So these in that particular alcohol. So these two are the applications of group frequencies. First is the structural identification of organic compounds, that is structural elucidation, and second is the detection of hydrogen bonding. Okay, and next we will come to rotational spectroscopy. So as we have mentioned earlier, rotational spectroscopy is caused by the absorption in the microwave region. Okay, so for a molecule to show a rotational spectrum, the essential condition is that the molecule must possess a permanent dipole moment. Okay, for molecules like hydrogen, chlorine, carbon dioxide, etc., there is no permanent dipole moment. Therefore, these molecules will not give rotational spectrum. Whereas in the case of molecules like HCl, carbon monoxide, HBr, NO, H2O, CH3Cl, ammonia, etc., all these molecules possess a permanent dipole moment, hence they are microwave active. That is, they will absorb microwave radiation and will give microwave spectra. Okay, so microwave spectroscopy or rotational spectroscopy, it is concerned with the study of pure rotational motion of a molecule, and it arises from the interaction of the molecular dipole moment with the electromagnetic field. And if the molecule has no permanent dipole moment, the spectrum will not be obtained. And when the molecule having a dipole moment rotates, what happens? It generates an electric field, and this electric field generated by the molecule will interact with the electric field of the microwave radiation. Okay, as a result, energy can be absorbed by the molecule, and thus the rotation of the molecule will give rise to the rotational spectrum. So this is the principle of rotational or microwave spectroscopy. And the rotational spectrum occurs in the microwave region of the spectra and is termed as microwave spectroscopy. And the region for microwave spectroscopy extends from 100 micrometer to 1 centimeter. So this is the range of microwave spectra. Now let us see the rotational spectra of a diatomic molecule. So we are considering a diatomic molecule, and this diatomic molecule is rotating. We have to imagine a rotating diatomic molecule, and it is treated as a rigid rotor. Okay, it is treated as a rigid rotor, and consider two atoms of masses m1 and m2. Okay, and these two atoms are chemically bonded to form a diatomic molecule by a rigid bond, and in this case the bond is rigid. Okay, and let R be the total distance between the center of mass of the two atoms m1 and m2, and R1 and R2 be the distance of the atoms from the molecular center of gravity, and C is the bond length. So this R will be equal to R1 plus R2. So you can see a figure here, a diatomic molecule, and the bond length is R, and from this equilibrium center of mass, equilibrium distance is R1 and R2. So this R will be equal to R1 plus R2 here, and at center of gravity of that molecule, M1 R1 is equal to M2 R2, and the moment of inertia, that is represented using capital I here. The moment of inertia is given by capital I is equal to M1 R1 square plus M2 R2 square. This is the formula of moment of inertia. Now you have to substitute 1 in 2. So here this is equation 1, you have to substitute this 1 in 2, that is the value of R2 in this equation 2. So M1 R1 is equal to, the equation becomes M1 R1 is equal to M2 into R minus R1. So this is the value of R2. So we are expanding this equation and we get M1 R1 is equal to M2 R1 minus M2 R1. Sorry, M2 R minus M2 R1. That is M1 R1 plus M2 R1. You have to bring this term to the LHS. M1 R1 plus M2 R1 is equal to M2 R. Therefore, R1 into M1 plus M2. You have to take this common factor R1 outside, and this becomes R1 into M1 plus M2 equals M2 into R. Therefore, R is equal to M2 into R divided by M1 plus M2. So this term is sent to the denominator. Okay. So this is the expression for R1. Similarly, an expression for R2 can also be derived as R2 is equal to M1 R divided by M1 plus M2. So now you have the equation for R1 and R2. Now we have to substitute the values of the expression for this R1 and R2 in equation 3. This is the equation for moment of inertia. So the moment of inertia, that is capital I, will become like this. I is equal to M1 into R1. In the place of R1, you have to substitute M2 R divided by M1 plus M2 plus M2 into, you have to substitute the value of R2 here, that is M1 R divided by M1 plus M2. So the equation, after so many steps, we will get the final answer as I is equal to M1 into M2 into R square divided by M1 plus M2. So here we know that I is equal to mu into R square. This is the formula for the moment of inertia. Here mu is the reduced mass which is given by M1 M2 divided by M1 plus M2. So this is the formula for mu, reduced mass for a diatomic molecule. Okay, so you have to learn by heart these equations. I is equal to mu into R square. So the rotational energy levels allowed to the rigid diatomic molecule can be calculated from the Schrodinger equation. Just like how we saw the vibrational energy levels allowed for a simple harmonic oscillator. In that case, previous case also, we applied a Schrodinger equation for vibrational motion, and we derived the values for vibrational energy. Okay. In the similar way, we can also apply the Schrodinger equation here for a rigid diatomic molecule, and we can derive the rotational energy levels allowed for a rigid molecule, okay, diatomic molecule. So this is the equation for that is Ej is equal to h square divided by 8 pi square I into j plus 1 in terms of joules. Okay, so this capital J is the rotational quantum number, and it will be having values like 0, 1, 2, 3, etc. And h is a Planck's constant, and I, this is not L, this is capital I, this moment of inertia. So the capital I moment of inertia is given by mu R square. Okay, so from this formula you know the expression for capital I. So this is the term capital I here. And it is customary to express the energy in centimeter inverse rather than in joules. So when we do the problems, we have to express this in terms of centimeter inverse. Okay, the energy value is calculated in terms of centimeter inverse. For that we have to divide this formula, divide this energy value by Hc. Okay, the term Hc will have to be added to this expression. So this expression will become E is equal to H by 8 pi square Ic into j plus 1 in terms of centimeter inverse. Okay, so both this formula you have to learn. And this particular term, that is H divided by 8 pi square Ic, this is equal to capital B, that is a rotational constant. Okay, so this equation will be converted into E is equal to Bj into j plus 1 centimeter inverse, where B is equal to H divided by 8 pi square Ic in terms of centimeter inverse. This is the unit of the rotational constant B. Now we can put the values of J. If you are putting different values like 0, 1, 2, etc. in equation 5, we are putting different values to this rotational energy level, we can get the allowed rotational level of a diatomic molecule. So it is represented in this figure. Okay, you can see this rotational energy levels. So as I mentioned in class, the distance between this rotational energy level is increasing as we go higher and higher. So this is a figure, or each line is representing each rotational energy level. Okay, and the distance between these adjacent rotational energy levels, this is 2b. Okay, this distance is 2b. So these lines are obtained at 2b, 4b, 6b, 8b, etc. And all these lines are represented here. Okay, 2b, 4b, 6b, 8b. And you can see that the distance is increasing as we go from j is equal to 0 to higher levels. And in this case, important problems are there. That is, from equation 5 we get the rotational energy level, which consists of lines at 2b, 4b, 6b centimeter inverse, and the distance between two successive lines is 2b. So there's a various lines in the rotational spectrum will be equally spaced as shown below. So there is also a selection rule for rotational spectra. Just like we saw the selection rule in vibrational spectra, similarly there is selection rule for rotational spectra also. So this is the selection rule, that is delta J is equal to plus or minus 1. So only those transitions which obey this selection rules are allowed. Okay, that is why selection rules are there. So give the selection rule for rotational spectra. So the selection rule is delta J is equal to plus or minus 1. And now give the selection rule for vibrational spectra, delta J is equal to, delta V is equal to plus or minus 1. This is the selection rule for vibrational spectra. Now coming to this rotational spectra, you can determine the bond length from the data given in rotational spectra. Now let us see how we determine the bond length. Okay, so we know that the rotational constant, rotational constant B is equal to h by 2 pi square Ic. So from the rotational spectrum, which consists of a series of equally spaced lines, the value of B can be calculated. So if the spacing between these lines in the rotational spectra of a molecule is given, that is, if the value of 2B is given, we can know the value of B. Okay, so that is the value, the spacing divided by 2 will give the value of B. So B is equal to h by 8 pi square Ic. And we also know that this I is equal to h by 8 pi square bc. So we are bringing this term b to the denominator and we are taking this I to the other side. So here I is also given by another formula which we know, that is I is equal to mu r square. Okay, and from this if we want to calculate the bond length is r. Okay, the value of r. So if we want to calculate the bond length, we have to convert this formula to this form, that is r is equal to root of I divided by nu. And on rearranging, we are substituting the expression for I in this formula. So we know the expression for I is h by 8 pi square bc, and we put this expression in this formula for r. So on rearranging, we get r is equal to root of h by 8 pi square bc mu. So you know, this is an inverse relationship, isn't it? So the distance, the equilibrium distance r and mu. Okay, so this is the formula for determination of bond length of a molecule from the rotational spectrum. From the rotational spectrum, we can calculate the bond length of the molecule. Let us see a problem here. So the first problem, the rotational spectra of a pure CN molecule gives a series of equally spaced lines with interspacing 3.8 cm inverse. Calculate the bond length. Given the molar mass, that is for carbon it is 12 gram per mole and for nitrogen it is 14 gram per mole. So what is given here? Here the interspacing of the molecule is given. The spacing means the distance 2b. So the distance 2b is equal to 3.8 cm inverse, and from this we can obtain the value of b. So b is equal to 3.8 divided by 2, that is 1.9 centimeter inverse. Remember, writing unit is very important. There is marks for that. So you should not forget to write the correct unit for all these calculations. Okay, and now here now we have to take this formula. Now we know the value of b, that is the rotational constant, and now we have to calculate the value of I, that is the moment of inertia. For that we have to take this formula h by 8 pi square bc. Okay, and substituting all the values, that is the value of Planck's constant, rotational constant, and all these, c is the velocity of light. Okay, and all these in this formula we get the answer as 1.47 into 10 raised to minus 46 kilogram per meter square. So this is the value of capital I. Again we have to know the bond length, so we have to know the value of r. Okay, for that again we have to calculate the reduced mass. Okay, for reduced mass we know the formula as m1 m2 divided by m1 plus m2. That was a formula which we derived earlier. So in the case of a CN molecule, that is mc into mn, that is the molar mass of carbon and mass of carbon atom into mass of nitrogen atom divided by mass of carbon plus mass of nitrogen atom into n. So here there is a term n, that is Avogadro number. Okay, this is a must. You have to divide this value using n for calculating the value of mu. You should not forget to do this. That is, the answer is 12 into 14 divided by 12 plus 14 into this Avogadro number, and the value of mu is 1.07 into 10 raised to minus 26 kilogram. Now you got the value of mu in terms of kilogram. Okay, the molar the mass of each atom was given in terms of gram per mole in the question. Okay, you can see the question here, it was given in terms of gram per mole, and you have to derive the reduced mass in terms of kilogram. That is why you are dividing this with the moles, okay, Avogadro number. Now we have to calculate the value of R. For that, now we know the value of moment of inertia and the reduced mass. We have calculated that independently, and substituting all these values, these two values in this equation, we get the final answer, that is 1.172 meter. There is a similar problem. The answer is also given here. You have to try it for yourself. Okay. So this is a calculate the bond length of carbon monoxide molecule, and the rotational spectrum in which the energy difference between the successive absorption line is 7.61 into 10 raised to minus 17 joules. So you try it for yourself. Okay. And finally, you have some applications of rotational spectrum. It is used for the determination of bond length of a polar molecule. And a polar molecule means a molecule having a permanent dipole moment. Okay, remember, only these type of molecules will give rotational spectrum. And then you can determine the symmetry of the molecule, and also you can determine the dipole moment of gaseous molecules. So all these are the applications. So please work out all these questions given at the back of this unit. So for example, you can see problems like a molecule has 4 atoms, how many stretching vibrations are possible, or what do you mean by a near infrared region. So you know that the infrared region was first I mentioned that it was divided into 3 regions: near infrared, middle infrared and far infrared. So near infrared means it is near to the red region of the visible spectrum, okay, visible light, that is VIBGYOR. It is nearer to the red region, red side of the visible spectrum. It means a near infrared. So also there are also other questions like which molecules are IR active. Okay, so please do it for yourself. So these are all easy questions, and also there are essay questions and short questions here. The problems are very important. Calculate the bond length of CO molecule, just the problem we saw just now, and what you understand by molecular spectra. So all this, the relationship between moment of inertia of a diatomic molecule and the spacing in microwave spectra. You know the spacing is 2b. Okay, the spacing between the microwave the energy levels is 2b. The spacing is 2b. From that you can get the value of b, that is rotational constant b, and again from that you know the relationship between b and I, isn't it? So these are the expressions. I is equal to h by 8 pi square bc. So all these are important sections. Please do not miss these sections. Okay, so the problems, then interspacing, how this rotational spectra, all these peaks are spaced, and all the energy levels are situated at 2b, 4b, 6b, hb, etc. and these are all equally spaced at 2b values. Okay, these are the energy spacing. Okay, so that's all for this class. If you have any doubts, please contact me. Okay, thank you.